Wait, are we recording? Yes. All right, section 2.7, combining functions. All right, let's get these initial operations out of, oh my goodness, no, it's doing that focus thing again. Now, what I'm seeing right here is that it's cutting off the words I'm writing up top, but I checked the previous recording and it wasn't cut off. It's like it just zooms in while I'm in the meeting with myself, so I hope it's not cutting stuff off. Okay, 2.7, combining functions. Let's talk about the first four operations real quick about how we combine functions, and it's going to be exactly what you think it would be. So given two functions, f of x, g of x, we define the sum, excuse me, the sum f plus g at x, f plus g at the same x at a particular x, it's just f of x plus g of x. I mean, literally just add the functions together. Now, if you check the text, they're noting the domain issues here, but I'm not getting into domain issues. So any homework I've given you that if I give you any review problems from the back of this section to look at, and they say something about finding the domain of the composition or the combination of the functions, don't worry about that. We're not doing that. Okay, so if you want to find the difference of two functions at a particular x, you just subtract the functions. So what am I really saying here? I'm not really saying much. Right, products work the same way. If you want a product of two functions, you just multiply them. And if you want to divide two functions at some particular x, well, you just take the function f at x and the function g at x and you divide them. Okay. Examples. I mean, do I really need to say anything else here other than just running some examples, right? There's not a lot going on here. So example 1. Find, so here we go, find f plus g at x, f minus g at x, f times g at x, and f divided by g at x for, let's see, let's do, what was the one I gave? I don't want to pick exactly the same one. Okay, let's do 7 minus 2x and g of x equals, I don't know, x squared plus 4x. Okay, I'm going to solve it in green. Okay, here we go. F plus g at x, f plus g at x, f plus g at x. F plus g at x is going to be the same as f of x plus g of x, and that's going to be the same as 7 minus 2x plus x squared plus 4x. Combine like terms. That's all you got to worry about here. Combine like terms. So I've got a 7, I've got a negative 2x and a positive 4x. So when I add those, I'll get a positive 2x and then my x squared. And that's it. That's it. I mean, I could put it in descending order by exponent, like x squared plus 2x plus 7, but this is fine. That's fine. Okay, so that's that one. Then I've got f minus g at x. A little bit more careful here. F of x minus g of x. want to make sure that I'm wrapping that second function, wrapping all of its terms in parentheses, so I remember that I'm subtracting all of them. So I'm going to have 7 minus 2x, that's the f function, f of x, minus parentheses x squared plus 4x. So there's g of x inside parentheses there. My next step, I'm going to clean up those parentheses and go ahead and what I mean is distribute the minus sign to both of those. In other words, making sure that I'm subtracting everything from g of x, and I'm going to have a positive 7 hanging around. I've got a negative 2x and a negative 4x, so those are going to become more negative as a negative 6x, and then my negative x squared comes down. Okay. How about f times g at x? Well, that's the same as f of x times g of x. Okay, so here, I'm going to go ahead and do that. So here, I'm going to have, I already forgot what the functions were. 7 minus 2x, and I'm multiplying them, so I need to make sure I wrap both of the functions in parentheses to make sure I multiply all their terms by all the terms in both functions. So this is x squared plus 4x wrapped in parentheses here. This is going to be the most involved operation, right? Multiplying the two functions. This one's going to take the longest. I've got a 7 times x squared. So recall that the way that we do this multiplication is we take this first term and we multiply it by all the terms here. So 7 times x squared is 7x squared. 7 times 4x is 28x. And then we take the negative 2x, we send it to both of the terms. So negative 2x times x squared is going to be negative 2x cubed. Negative 2x cubed. Negative 2x times positive 4x is negative 8x squared. Look for like terms. I do see some like terms right here, this 7x squared and this negative 8x squared. 7 plus a negative 8 gives me a negative 1, so I'm going to write that as a negative x squared. That's my negative 1x squared coming from combining these two like terms, plus 28x minus 2x cubed. And that's fine. It doesn't need to be in descending order. If you really like, you can, if you want it in descending order by exponent, you can write it that way. So that's the product of the two functions, just multiplying them, cleaning it up, combining like terms. And the last operation, which you may be dreading, you may think, oh, this is going to be like the worst. Division is always the worst. But in general, it will be really as easy as just writing one function on top of the other, because often there's not going to be anything else you can do. So literally copying f of x over and g of x over, and that's it. I guess the only other thing we should maybe note here, if we wanted to, even though we're not really talking about domain issues here, but we could say, note that x cannot be 0 here because 0 in the denominator would give us a undefined, right, division by 0. And also, what other value can it not be? What about negative 4, right? Negative 4. How do I get these? How do I know? I set that equal to 0. So this is going back a bit, right? But how do I solve this? When I say this is going back a bit, I mean we haven't thought about this kind of thing in a while. Well, I guess we thought about it with the reciprocal functions and how their domains were restricted. Okay, so how do I solve this? Well, I say, well, I can factor an x out. And now I've got a product of two things equal to 0, so I can split that and set those equal to 0 independently. This equals 0 and x plus 4 equals 0 independently. Solve this last step here, so I'm getting x is 0, x is negative 4. Those are going to be the two values that output a 0 in the bottom here, hence they are my undefined values for x here, my domain restriction here. That's just kind of an extra thing here. Anytime you've got a rational function like this built, it's always a good idea to go ahead and write down what values are going to be domain issues, or are going to give you domain issues. Okay. That pretty much sums up the combinations of functions with those four operations. I mean, I could just do more examples, but that pretty much is it. Now let's really get into the meat of this section, which is composition of functions. And by the way, I'm not going to be asking you to graph combinations of functions, even though that's a lot of fun, but we won't be doing it. All right, so let's talk about composition of functions. A new way to combine functions. We've kind of already done it a little bit. So given two functions, the composite function f circle g, so that's f circle, that's not an O, that's like a little circle notation. It's like a multiplication symbol, but like not a closed dot, it's open. Composite function, or the composition of f and g, so this is also read as the composition of f and g, is defined by, so how do we define this? F circle g at x, so f, here's how I would read this. F composed with g at x is equal to f of g of x. Literally plugging the function into the other function. So this is, what are we doing here? We're plugging functions into functions. We've done this. We've done this before when we were evaluating functions and I had you plugging other functions into this is all the way back to 2.1, I think. We've already done this. We just didn't call it this. And there's a whole lot we can say about this, but for now, let's just practice using the composition. Let's actually do one, or do a couple. All right. Part A, find f composed with g at x. Part B, find g composed with f at x. Okay. Here we go. Use orange. Part A, f composed with g at x is equal to f of g of x. And you might say, well, that's not much more helpful, but it really is, because it tells you to literally write your function f of x, x squared plus 1, but in place of the x's you see, which is just this one, right, for f of x, just that x right there, you're going to replace that with the entire g of x function. So I'll write it like this. There. So literally replacing x, the little window into the function right here, x, literally being replaced by g of x. Okay, but what is g of x? G of x is 2x plus 3. Right, by definition up here. Yep, and what does this mean? This means we got some multiplying to do. So I'm going to take my equal sign and back it up a bit because this is going to expand out, right? So recall that to multiply this, you've got to expand it like that. And then you've got a 2 by 2 times a, so you've got a 2 terms by 2 terms. I'm going to go through this a little bit quick. So 2x times 2x is 4x squared. 2x times 3, so this 2x times this 3 gives me 6x. 3 times 2x is another 6x, and then 3 times 3 is 9. And don't forget the plus 1. The plus 1 just hanging out at the back. So recall that whenever you're squaring something like this, like a two-term thing that gets squared, what ends up happening? You end up squaring this outside term, getting 2x squared is 4x squared, right? Or 2x all squared is 4x squared. You end up squaring this outer term to get the 9, so 3 squared is 9. And then you end up doubling that central term. So you have 2x times 3 doubled, right? So I get 4x squared plus 12x. And then, of course, at the end, I'm going to add up 9 plus 1 to give me 10. So here's my final answer. Now, what am I talking about with this little, what was I just talking about with that doubling term? Recall the formula for squaring a sum. If you've got a plus b all squared, that's the same as a squared plus 2ab plus b squared. So that's what I'm getting at describing this. All right, let's find, so that's it, that's f of g of x. You plug in g into the f of x function and then you evaluate, which often means like expanding and then combining like terms. Let's look at the opposite direction. Do we expect, let me point something out back here. We expect which of these operations to commute, meaning which ones can flip, which ones can the order flip. Sums can flip, right? So, well, I'm not going to write anything here, I'm just talking. F of x plus g of x is the same as g of x plus f of x, right? That's how addition works. That's not how subtraction works, right? Like 2 minus 3 is not the same as 3 minus 2. So this commutes, but this does not. Multiplication does commute, right? Like 2 times 3 is the same as 3 times 2. But division does not. So already we're seeing right up front that some operations, the order can flip and you won't change the answer. But some operations, if you do change the order, then it's a different problem, right? It's a whole different thing. So how does composition behave? And we're about to find out right now. By finding g of f. G composed with f at x is going to be the same as g of f of x. So I literally write my g function. So let me get this here. Literally write g, but instead of an x, you're going to write f of x. 2 times, and wrapped in parentheses just to make sure everything that needs to happen to it is going to happen to it. Okay. So 2 times f of x, which is x squared plus 1 by the definition from the given, right? Oh, plus 3. Now this one's a lot easier, right? Just distribute the 2, 2x squared plus 2, and don't forget that 3. And then finally combining those like terms, 2x squared plus 5. A lot easier, that one, right? It's a lot easier than the first one. And it's not the same. See, this is not the same as that. So the operation does not commute. The operation of composition does not commute, meaning that we cannot expect f of g of x to be the same as g of f of x, except maybe possibly in very special situations. Maybe we'll investigate that. All right, let's look at some weird examples here. What was that? Okay, example 3. Let's consider, hang on. Okay. Oop, 1 second. What is happening? There we go. Okay. I'm just going to say evaluate each. These are some, these are legitimate problems. They're just a little different, so it can take a little bit to wrap your head around. All right. If g of 8 is equal to 10 and f of 10 is equal to 15, then what is f of g at 8? Okay. Well, start with this, f of g of 8. F circle g, so f composed with g, not at x, but at 8, literally one particular number. That's going to be the same by definition as f of g of 8, right? Just by definition. It's not an x, it's an 8. That's okay. But look, what is g of 8? It's 10. So literally this g of 8 gets replaced by the number 10. F of 10. Well, what's f of 10? It's 15. It's 15. That's it. It's 15. F composed with g at the number 8. They've set it up, right? It's like setting up dominoes and asking you to kick it over, right? That's a problem like this. Sometimes it stumps students so much because it's like almost too easy, right? This is one of those problems that almost seems too easy. They're setting up the steps so that you can plug one directly into the other and then everything just kind of falls right out. You just have to look back up here and say, oh, g of 8 is 10. Oh, and f of 10 is just 15. All right, let's try maybe like a similar one where we're asked to evaluate at a particular number. But this time I'm going to say let f of x equal 2x minus 3, g of x maybe equal 3 minus x squared. Let's find f composed with g at -2. And let's find g composed with f at -2. Okay, f composed with g at -2. Well, how can I do this? What's going to be the easiest way? I have options here. I can either find f of g at x, right? Like compose them how I did example 2, which was a fair bit of work, right? Or I can just find what g of -2 is and then plug that in. So let me show you what I mean here. F composed with g at, so I'm doing this left-hand one first, right, is equal to f of g of -2. So what I'm going to do is I'm going to figure out what g of -2 is. So off on the side, I'm going to say, well, g of -2 is the same as 3 minus -2 squared, right? Just evaluating g at -2. That's going to be 3 minus -2 squared is 4, so 3 minus 4, and that's giving me a -1. Okay, that's g of -2 is equal to -1. That goes in right there. So this is now equal to f of -1. Let me number this problem I in this problem. So 1 and 2 there. Okay, so we're working number 1 right now. Just to keep that straight. Okay, so f of -1. Well, I just plug in -1 into the f function. All right, 2 times -1 is -2 plus 3, so -2 plus 3, and that's going to be 1. All right, cool. So f of g at -2, f composed with g at -2 equals 1. All right, now let me do part 2 here. help. Yeah, that's fine. Let's see. Okay, so G composed with F at -2 is what we're finding here. So first I'm going to need to go off on the side. Oh wait, first, let me write what the definition of this is. It's G of F at -2. So off on the side, I'm going to figure out what F of -2 is. Do I have that from my previous problem? No, I have F at -1. No such luck. Okay, so I got to do it by hand or manually, not just by looking at the previous problem. F at -2 is going to be, oh, wait a second. Did I do, look at that. What was I doing? Look at that problem. I added 3. It's supposed to be -3. Right from the function 2x minus 3. I think I was thinking about a function we worked earlier. So that should be minus, and that's going to change that to a -5. Sorry. Okay. Okay. So anyways, with the right function written down, 2x minus 3. So 2 times -2 is -4, and then minus 3 gives me -7. That's this input here. So f of -2 turns into just a -7. And now I say, oh, look, g of -7. Well, that's the same as 3 minus -7 squared. And that's going to be the same as 3 minus 49. Which is the same as -46. So that's the answer to this one. Let me go peek at Teams because I'm on a, okay. Okay, I thought it had stopped recording. I'm looking at WebAssign right now, just looking at some problems that they like to give. Huh, yeah. All right. A couple more examples here that we need to look at. What is this? Example 4, right? Because that was, yeah. All right, example 4. Actually, let me do a more complicated one. Let me do f of x equals 3 minus 3x squared. Find f composed with itself at x. Is this possible? Yes, of course it is. Just going to plug the function into itself. Just going to plug the function into itself. So I'm going to say, first of all, by definition, f composed with f at x is equal to f of x. So I'm literally going to write the f of x function, 3 minus 3, and instead of x squared, it's f of x squared. Okay. That's going to be the same as 3 minus 3 times f of x, which is 3 minus 3x squared, and then all squared. Okay. So pause the video if you need to, but look, all that happened is this 3 came down, the minus sign came down, this 3 came down, the square came down, the parentheses came down, and the f of x changed. This f of x turned back into 3 minus 3x squared, which is what it's defined as up here. Now I need to expand this, right, via squaring it, and then I'll multiply in the -3, and then I'll combine like terms. So I'm going to back up my equal sign, say 3 minus 3, and here I'm going to have 3 minus 3x squared times 3 minus 3x squared. That's what this square does up here, right? Definitely an exercise in your ability to stay organized here, right? Okay. 3 minus 3. So this 3 does not get multiplied until I'm done expanding this. Okay, so I'm going to have 9 minus 9x squared. That's from sending this 3 to both of these terms. And I'm going to send negative 3x squared to both of these. So negative 3x squared times 3 is another negative 9x squared. And then finally, I'm getting a positive 9x to the fourth. Going to combine some like terms inside the parentheses here. Those two negative 9s double down to make a bigger negative, in particular a negative 18. Right? Okay, now I'm going to send this negative 3 in. So negative 3 times 9 is negative 27. Negative 3 times negative 18 is positive 54. I don't know why I wrote a 2. 54x squared. Then negative 3 times this line will give me another negative 27 with that x to the fourth attached. Now, finally, I'm ready to combine some last like terms. 3 minus 27 is going to be negative 24. Then plus 54x squared minus 27x to the fourth. It's quite a bit, right? But that's kind of as worse as it can get. Plugging a square function into another square function. That's kind of the worst that we're going to deal with. Okay. Moving on. Again, moving a bit faster since this is a recorded video and I know you can just pause if you need to. Final example here I want to look at. You know, they don't even talk about this in the text, I'm pretty sure. It's, yeah. Oh, yeah, they do. Never mind. Yeah. Okay. Very small, though. Here we go. Express the function f given. So f is, dang it, capital F of x is equal to x minus 5 all squared. As a composition, so now I'm asking you to decompose the functions. Okay, so I'm asking you to look at this and recognize that this is one function plugged into another. The inner function, hopefully it's easier to note that the inner function is the thing literally happening on the inside. The inner function, which by the way is g of x, little g of x, right? Coming from, how do I know it's the inner? Well, it's the one that comes second here. The inner function is x minus 5. What about the outer function? What's happening on the outside? What is happening to g of x? It's being squared, right? How do you represent a square function? A function that takes in inputs and squares things. It's just x squared. Just x squared. It's the input squared. So to confirm now, if I take f composed with g at x, that's the same as f of g of x. So I'm going to literally write my f function, which is takes things in and squares them, but instead of x, I write g of x. And then squared, right? That's what the f function does. And then that's the same as x minus 5 squared, which is exactly what they wanted here. I don't need to expand it. That's not what this problem's about. It's about just taking a function that's written as already a composition and decomposing it into like two smaller pieces, or not smaller necessarily, but maybe simpler pieces. Now, in WebAssign, they ask you a very similar question to this, and they want you to give your answer. This is how they say. They say, oh, they also say use non-identity functions for, don't even worry about that. Yeah, just don't worry about that. Okay, enter your answers as a comma separated list is what they say. So they give you this. They give it to you like as a coordinate point, which is a little bit weird. And then they give you the box to answer it in, and they want you to answer it. They give you like a box with parentheses like this, and they want you to plug in f and g in order, f and g, right? F then g separated by commas. So you would say x minus 5 comma x squared. That's how you would input your answer. It's a little bit weird, but that's just how WebAssign wants you to plug in the answers here. Really, ideally, they should have asked like just two answer boxes, F and G, but whatever. That's how WebAssign wants it. So yeah, when they say use non-identity functions for F and G, you'll see that when you go look at this homework. They're just saying, because what you can do is you can just say that the inner function is just X and then make the outer function just exactly match this. And that's kind of like the cheating way to just write any function decomposed. So that's why they're telling you not to do that, because that kind of gets, it's not wrong, but you're getting away from the point that you can pull this function apart, decompose it into two simpler functions. All right, there's another one like that I will leave to you guys. You can always ask me about it later. The very last problem in 2.7 might be a little tricky, but you can always ask me about it. All right, that is it for, let me see, anything else I want to say for 2.7? For 2.7, yes, that special situation where f composed with g at x. I want to note something. If f composed with g at x equals x and g composed with f at x equals x, then the functions undo each other. This is going to be the point of section 2.8 when we talk about inverse functions. But I just want to give you a quick example, because since we're talking about composition, I want to just give a quick example. Consider f of x equals 2x plus 3 and g of x equals x minus 3 over 2. Just had to have a little think about that one. I don't know why. Anyways, so as an extra exercise, plug these into each other. Find f composed with g at x and g composed with f at x. Whoops, g composed with f at x, and you'll find that they both just end up yielding an x. Right, so the functions undo each other. You input an x into the function, and well, right up here, you input an x into the composition and it just spits it right back out. You input an x into this composition and it just spits that input right back out as if nothing ever happened to it, because f and g and f and g, they undo each other. Okay, so try that as an extra little example there, and that'll kind of set the stage for the next section of discussing inverse functions.